Welcome to Regents Review Unit 10, and we're going to look at kinetics and equilibrium. When we talk about this unit, we have to focus first on this idea of effective collisions. You have to envision the particles are constantly colliding, and sometimes they collide in the right way, and that an actual reaction occurs. So in order for a reaction to occur, reactant particles must collide effectively, meaning they must have the right amount of energy and the right orientation. So if we look at these particles here, in order for them to react and form these two new substances, they have to have the proper energy, we call that the activation energy, to get the reaction going, and also the right orientation. So if these particles were, let's say, linear and they collided, then we wouldn't get the formation of these two HI molecules. So they need this orientation to be correct as well. So not every collision is going to be effective. So once we have these effective collisions going on, how can we speed up that reaction rate? Well, the first thing we can do is use a certain type of reactant. The fastest is going to be an ionic compound that's dissolved in water, so aqueous solution. It's going to happen the fastest because it's already dissociated into ions, and therefore all we have to do then is just recombine them and make a new compound. So we're taking one of the steps away in comparison to a covalent compound. So it will happen faster. As we focus on these factors, let's think about, and we'll see in these diagrams, let's look at this idea of collisions. So if we have more effective collisions, we can increase the reaction rate. So the first one is increasing the concentration. If I have a low concentration and now I add more particles, higher concentration, I have a greater chance of these particles colliding, greater chance of effective collisions, and so the reaction rate increases. Increasing temperature from cool to hot. If the particles are moving faster, they have more energy, and they're also colliding more often. So hitting those two important factors for effective collisions. So the reaction rate will increase. If we have gases, if we increase the pressure, so here's an example here, as I increase the pressure, I'm essentially pushing the particles closer together. So it's like increasing the concentration, because we have more particles now in a given space, and therefore more chances of effective collisions, and that reaction rate increases. Increasing the surface area, so going from small surface area to large surface area, means I have more particles colliding and therefore reacting, and that's also going to increase our reaction rate. And the last thing we can do is we can add a catalyst. And what a catalyst does is provides that alternate pathway for the reaction to occur. And what it really does, if you look at it, is it lowers the activation energy. It lowers the amount of energy needed for an effective collision. So we have a greater chance of that reaction happening, and it happens at a much quicker rate. Looking at reactions, we have two basic types in terms of energy. We have the endothermic, where energy is absorbed, so it is on the reactant side, the left side of our arrow. And if you look at table I, on the bottom it tells you that a minus sign indicates exothermic, so a plus sign indicates that this reaction, in this example here, is going to be endothermic. That means the energy is going to be on the left-hand side. So I could rewrite, instead of energy, I could write 182.6 kilojoules over here. We're absorbing that. That energy is needed for this reaction to occur. Exothermic, exo like exit, and again therm meaning heat, that means heat is released as a product. So the delta H is negative, as we saw here at the bottom of table I. Exothermic reactions are more stable because we're getting rid of some of this energy, so we're going to a lower energy state or configuration, and therefore it is a more stable situation. Exothermic reactions are also spontaneous because they don't need as much of an energy input as an endothermic reaction. So if we look at a reaction, how do we know it's exothermic? Well, either we look up the delta H on table I and it's negative, or we see that energy is on the right-hand side. It's on the product side. It's being produced or released. And so in this case, we would actually feel this energy. If it was heat, we'd feel it as being hot. So looking at table I, again indicating that a minus sign is exothermic, you'll see the negative sign here, so negative 393.5. and if we were to place this value in our reaction, we would actually put it right here. We put plus 393.5. Notice that I didn't say negative. We don't put a minus sign in the equation. We put a plus sign. The net minus sign, that loss of heat, is indicated by the fact that we're placing it on the product side, the right side of the reaction. What happens if the reaction you're given is the reverse of what's on table I? So for example, is this reaction endothermic or exothermic? So water decomposing through electrolysis into H2 plus O2. Well, if I look on table I see it's reversed. Table I, it is a synthesis reaction, not decomposition. And so what do? Well, the delta H is still the same. The amount of energy changing from products to reactants is still the same in terms of magnitude, the amount, but the sign switches. So instead of being negative exothermic, it would be positive endothermic. So it would be positive 571.6 kilojoules. And that energy would be placed on, up here, on the reactant side. Looking at our potential energy diagrams, make sure that you can label both diagrams, so endo and exothermic. So at the very basic part of it, be able to draw an endo versus exothermic graph. And these are very simple. You never go to zero because we always have energy in the reaction. For endothermic, endo taking in energy, that means you end up with more energy at the end in your products. So product side must be higher than reactant side. And then exothermic is the opposite. Exo, exit, energy is being released, so we end up with less energy on our product side. And that's why this is a more stable type of reaction. The energy to get the reaction going. So you're always starting out the reactant. It always has energy. And for the reaction to actually take place, that effective collision, we need this activation energy. So this is the energy to get over the hill. Once we get to the hill, that's when we have breaking and reforming of bonds, and then the reaction takes place. So notice in the endothermic, it's a much greater hill than exothermic. This requires a lot more energy to get going, and that's why exothermic happens more often, and that's why it's spontaneous. The activated complex is essentially how much energy is at the highest point, so it's going from 0 all the way up. The energy of our reactants is going to be how much energy do they start with. The energy of our products is how much energy do they end up with. And then our delta H from table I is essentially the difference between our product energy and our reactant energy. So essentially it's the change in energy from beginning to end. What are the effects of adding a catalyst? Well, a catalyst lowers the activation energy, and it does that by providing, as you see in the red line here, an alternate pathway to get to our production of our products. And since it requires less energy, less activation energy, it happens faster and more often. On our regions, they often ask you to draw in with a dotted line what a catalyst would look like. An important thing to note is that we always start and end at the same place. So for example, if you're trying to, let's say, go to your house from school, and you go down one street, you make a left on the next street, then you make the right on the next street, and then finally you get home. So a catalyst would be like if there was a path through the woods that's directly to your house. It provides an alternate pathway that's faster, requiring less energy by you, but you're still starting at the same place and still ending at the same place. So the same thing happens in the reaction. So just make sure that when you draw your dotted line that you are starting at the reactant and ending at the product. We've also discussed entropy in lots of detail. And we've discussed it in many ways. Things like entropy is a measurement of disorder. And so as we go from solid to gas, gas is more disordered, so it has higher entropy. But in reality, entropy really is how many possible ways can we arrange these particles. And so we call these things microstates. And so if you look at a solid, since it's very rigid and very structured, there's not many ways we can orient these particles or arrange them differently. And so they have low entropy. As we get from liquid then to aqueous then to gas, we see gases have the most entropy because there's so many different ways we can orient these particles or arrange them differently, and that's why they have higher entropy. Notice that aqueous is higher in terms of entropy than liquid because we have more particles dissolved. We have two different types at least of particles that are in the situation, and so therefore more possible ways we can arrange them, and that's why the entropy is slightly higher than liquid. And lastly, we focus on equilibrium in this unit. Now, equilibrium is when the rate of the forward reaction, in this case going this way, equals the rate, again the speed, of the reverse reaction going this way. So the rate at which the product is forming and the rate at which this product is then breaking down back into the reactants becomes equal. What's not equal typically is the concentrations. The concentrations become constant. So rates are equal, concentrations are constant. Here's an example of equilibrium. Here is a phase equilibrium where water liquid is turning to water gas. So if we have a stoppered flask here, and you can see as the liquid water evaporates and turns to a gas, eventually that gas is then going to recondense back to a liquid. And when we reach equilibrium is when the speed at which this is occurring equals the speed at which this is occurring. So it may appear nothing is happening at all, but the reaction is still taking place. It's just at equal rates. So the example I gave in class is like if you're walking up a down escalator at the mall, if you're walking up at the same speed as what the escalator is going down, then it may appear that you're not moving at all, but in essence, yes, you're still continuing moving, it's just at the same rate. So if we're looking at this graph here, as the concentration of our reactant goes down, it gets used up, we make our product, and eventually when we reach equilibrium, you see that the concentrations become constant. So this is how we know, and we know where equilibrium is, when these lines are flat, again indicating that constant concentration. And the last thing we can focus on is Le Chatelier's principle. Le Chatelier's principle is about equilibrium shifts. So when we stress the system, we can shift equilibrium more towards the product side, making more products, or more towards the reactant side. And so Le Chatelier's principle states that when you increase a concentration, for example, we add a stress, equilibrium shifts away from that stress, that side, to relieve it and restore equilibrium. And when we take away, for example, decreased concentration, we take away a stress, equilibrium is going to shift back towards that side, again to restore equilibrium. So here's an example of a reaction, and we're going to go through all the different stresses that we can use here. So it's add away, take away towards. So if we increase the concentration of any of these reactants, either CO or O2, increase the concentration, so we're adding to this side, the reactant side, so it's going to shift away from this side towards the product side. We're going to make more of our products. So add away, we're going to end up making more of this. So the concentration of CO2 goes up, as well as the heat energy. We're going to produce more energy. And over time, these are going to decrease. They're going to go down because they're getting used up to make all this stuff. So add away. If we decrease the concentration of any of these things here, the reactants, take away, it's going to shift back towards this side to restore equilibrium. And therefore, all of this stuff goes down, and all of this stuff is going to increase. And then the same thing's going to happen on the product side. So again, it's the same concept for Le Chatelier. When you add a stress, it shifts away from it. So add away, take away towards. So if I focus on the product side, if I add more CO2, so increase the concentration of that, or if I increase temperature, the heat, since it's on this side, it's like just adding more concentration. So adding more of these, it's going to shift away from this side to the other side to relieve that stress. So therefore, all of this stuff is going to increase. And of course, then this decreases because we're using it up to make these substances here. And then take away towards, so by decreasing any of these things, so either decreasing concentration of CO2 or decreasing the temperature, take away towards, it's going to shift back towards this side to restore equilibrium. So everything over here starts to go up and increase, and then everything on this side decreases. So whatever way you're shifting, right, whatever way you're shifting, if I'm shifting to the right here, then the arrow in terms of this equilibrium here is going to shift to the right, and so whatever way it's pointing, that stuff goes up, and then the other side has to decrease in order to make that. Looking at pressure only affects gases, so you have to look at the reaction and say, is there any gas involved? In this case, yes, there is. The next question you ask is, which side has more moles of gas? So we can count them up. This side has 2 and 1 is 3 moles of gas on the left and only 2 moles of gas on the right. So this side is affected more by the increase in pressure. Once you've established that, then any change that you do is going to be focused on this side. So if we increase pressure, add to this side, it's going to shift away from this side to the right, to the product side, and make more of this. All this will go up, and this stuff will go down. If I take away pressure by decreasing it, take away from this side, it's going to shift back towards it to replace it and restore equilibrium. And so therefore everything over here will have to go up, and everything on this side will start to decrease. So what can we conclude about equilibrium from our graph? So here's an example of a equilibrium reaction. Again, notice the double arrow representing equilibrium. And we can see here this graph represents this reaction. So initially we start out with CO and O2. Here's CO, here's O2, and we have CO2 here. Notice the lines are constant or flat. So concentration is constant. We've already established equilibrium, this reaction here. So this reaction, the forward, is equal to the reverse. Now, what happens when we add a stress, like we just talked about? Well, if we increase the concentration of CO, it's on the reactant side. So add to this side, it's going to shift away from this side to the product side. So this stuff is going to then increase. And we can see that here. So I initially increase the CO, and watch what happens to CO2, this side. It starts to increase. What happens to the side where I added? That starts to decrease, because that is being used up. The CO and the O2 are being used up to make the CO2. And then notice, again, it reestablishes equilibrium. It's just now closer to the product side. And we know it's equilibrium because these lines are flat, and that's our concentration. The concentration, again, becomes constant.